So this is the last part of the second lecture, and we talk about the truncation area. I want to give you one example of a truncation. And we do that for a function that we know absolutely precisely. We know the function and we know the derivative. And this is the sinusoidal function. Sinusoidal function, which we call a test function. And let's have a look at it. Test function, f is a function of the location x, and the function looks like this. It has an amplitude called a, and this one is just set to 1. Okay, so you don't need to worry about it. And then you have a sine, and the sine function is depends on the location x that you have, and it has something like 2 pi, and it has something that we call lambda, the wavelength. Okay, and the wavelength is a given constant that you plug in, and we choose 100 meters. And then you can plot this function. It only depends on there's no time development or no evolution at all. Okay, it's just a stagnant function. And it's shown here. So the function varies between +1 and -1 on a wavelength of meters. Wavefinder for 100 meters, you get a complete cycle, going up, going down, going back. And then you can work out the spatial derivative. And if you ever done that at high school, if you do the spatial derivative, you actually have to take the inner derivative times the outer derivative. It's known as chain rule, okay? You have to do that, and then you work it out, spatial derivative. And you can plot it. You plot this function too, and what you see is that this one is the slope of the function f, and you get the slope is 0. You get the crossings of 0 wherever you have either crest or a trough. This is where you have then you either have a positive slope or a negative slope in between. That's all there is, okay? So now the next step is we want to represent this function by finite differences. Okay, we know exactly this function. Work out this function and finite derivative and work out this spatial derivative. Okay, and this one is now done here. So the top line shows you the original function and the first derivative. And now what we do is we use the spatial derivative using centered difference. And you just learned what that is, centered difference. Okay, shown here on the left. This is the centered difference. Functional value at location x plus delta x minus functional values location minus delta x divided by 2 times. And then you plug in the function. This is what you do here. You plug in the function that we have, test function. You just write it down. And then you consult some textbooks because you want to re-modify, and you learn that you can actually simplify it, and you work out actually it can be derived, it can be written in this form. This is the total form, and what you see is that the first part is exactly the analytical. I highlighted this by the red rectangle, and you get exactly the same thing, but you get something a little bit different. Times 1, that's not a drama. 1 is just, if you multiply something with 1, you get exactly the same thing, but there is an error. Minus, I call it epsilon, x, and you can actually work out exactly what this error is, and it's written here next to my shoulder. This is the error. Okay? All right, this is the error. Error depends on the grid spacing, delta x, relative to the wavelength. You can see this is a ratio, delta x divided by lambda. It's the ratio between the grid spacing and the wavelength. It actually tells you how many grid points do you have within the wavelength. Okay? what is your resolution? How many points do you resolve your wavelength? So you get an error through your choice of delta x. If you know what the wavelength is, what is the rule of thumb? How many grid spacings have to fit into your wavelength? Let's have a look at that on the next slide. And here it shows you the error. So this is the analytical solution at the top. This is the slope of your function, gradient, the first derivative. And the bottom graph shows you the solution using finite differences for 3 different grid space. The red curve shows you the choice of the grid spacing of 10 meters. What it means is that there is a 10 grid points within the wavelength. The wavelength was 100 meters. You have 10 grid cells covering your wave. And you get this, the first derivative looks pretty good. You almost follow the analytical solution is the black line. Okay, now what you do is you decide, oh, I don't need 10 meters. I just use 30 meters. If you do that 30 meters, all of a sudden your gradients, your first derivative looks much worse. You still get the positive and the negative. But if you choose 60 meters, for example, you get it terribly wrong. You even get the sign wrong. So the rule of thumb is from this consideration is that the grid spacing must be chosen small enough to spatially resolve the process of input. And the rule of thumb is that the grid spacing should be 1/10 of the wavelength of a field, or better if you can. So this is a rule of thumb. It's really important.